Okay, so we left off yesterday. By saying where will an electrophile go on a 6-member, this is called pyridine. So on a pyridine ring, where will the E plus add? Will it add to A? Will it add to B? Will it add to C? Will it add to a combination of those? And so the only way we can determine that is by adding E to carbon A, writing all the resonance structures, adding it to B, writing all the resonance structures, and adding it to C, and writing all the resonance structures. And then the one that has the most resonance structures is going to be where E plus adds. So which one had the most resonance structures? B? How many resonance structures did B have? Do you have 3? 4? Okay. So let's go ahead and just add to B. So if we add the pair of electrons, or we use the pair of electrons to bond E. So adding to B, we're going to have an H and an E with the plus charge here. And then that's going to be our first resonance structure, right? So then what am I going to do next? So which pair of electrons do you want to move? I can't do, if you want to move this one, we can't do that now. Because there's no place for us to move it. The only place I could move it would be here or here. And I can't move that pair of electrons because those carbons already have 4 bonds each.
If you move the bottom.
Okay, so you want to move the bottom where? Right or left? Like that? Okay, I can do that. That I can do. We haven't even started yet. And you're yawning. This is not good. I know. I told Melissa I'm just like everybody's beaten up at this point, including me. But we still have to suck it up and make it through. Okay, so is that one, did everybody have that one?
Why you can't move the bottom one and then the top
Well, I can only move one at a time. So I'm just moving the bottom one, right? And then I'll move the top one next. So this will make resonance structure number 2.
Where was the second double bond in the structure on the left?
The second one is here.
Oh.
So there's two right there. This one and this one. So what we did was we moved the one attached to the nitrogen over one. That puts the plus charge there. Okay. Now can we draw one more? Yeah, we can draw one more by moving that pair of electrons there. And so that'll get us to the third one. So we've got an H here, an E here, we've got the plus charge there, and then the double bond here and here with the nitrogen. So that's 3. I heard some people say they had 4.
I have 5.
Oh, you have 5. Well, let's do the 4th one first.
So you just move the bond.
can't move the bond again. Because, no, I can't move that one. So what was number 4 then?
At one point, I moved the loan pair.
The loan pair on,
Well, from our first transition, instead of moving the bond, I actually.
okay, this one, this structure?
Yeah.
Okay, and what did you want to do with
I
that?
put the same place with the double bond.
So you want to take, let me rewrite that structure. So what you would like to do is,
So I put the lone pair to the right.
so take this lone pair on the nitrogen and move it like that.
I put plus.
Okay. So you're going to have something that looks like that.
Yeah.
Did anybody else do that? You didn't do that? What was your 4th? So on this one, you move this H. You lost it? So you did a hydride shift. I don't think that's allowed. And I'll tell you why. Because if I do that, and if I make the hydride shift, I'm gonna end up with the H here, and I'm gonna end up with my double bonds in these positions, my E here with my plus charge. I suppose I could do that. And then, let's see, so then I'd have 2 H's here, right? So then my final step, I would have to lose the H plus. And if I lose my H plus, then I'm going to get my final product, which is actually what's going to happen here. I'm going to lose my H plus to then give me, to reform the aromatic ring, but now substitute the electrophile there. Technically, no. So resonance structures, you're only allowed to move pi electrons or lone pairs. You're not allowed to actually break a bond. So this would technically not be a resonance structure. This is not an additional resonance structure because you broke a bond. Now, we normally don't do that. We normally don't actually do a hydride shift. And our rule for the hydride shift would have to be that the electrophile, that having the plus charge next to the electrophile would be a more stable structure. And I could see that happening, bless you. I could see that actually happening. So we're going to discount it, not because it couldn't happen, because I think it could. So I'll take back my earlier statement that says, no, we can't do that. We can, but it won't be a resonance structure. Because in breaking this carbon-hydrogen bond, I'm not doing a resonance structure. So this would not be a resonance structure. Would it exist? I honestly don't know. So that's okay, it just wouldn't be a resonance structure. So if that was your 4th one, you basically have 3 resonance structures. Anybody else have any other resonance structure other than, let's say, A and B and C, and then some people had D? Any other ones that anybody had?
So D is not.
Well, let's talk about D. Is D stable? Why not? Why don't you think it's stable?
Because because it does more.
Stick with the positive charge on nitrogen.
Oh.
Is that a stable situation?
No.
Is it stable to have a positive charge on nitrogen versus carbon? No. So that's one strike against D. Is it a resonance structure? Yes. The question is it a stable resonance structure? So strike one is nitrogen has a positive charge. I would say strike two is that what would be the geometry of that nitrogen atom? So it's a nitrogen with two double bonds and no lone pairs. So so this takes us all the way back to the beginning of the summer, or all the way back to when you took Organic 1, which might have been a long time ago. So that nitrogen has two single bonds, two sigma bonds, and no lone pairs. So that means its hybridization is sp. We agree, we don't agree. So that's sp hybridized. What is the geometry that goes with sp hybridization? Be linear. Is that nitrogen linear? No. Is that stretching the bounds of linearity to be in a six-membered ring? Yes. So this would kind of fall under, like, why was the benzene so unstable? Because I tried to put a linear molecule or a portion of a molecule into a six-membered ring. And that didn't go over well. So in this case, this resonance structure has two strikes. Nitrogen with a positive charge, nitrogen sp hybridized. So is it likely to exist, or is it likely to contribute a lot to the hybrid? No. So really we only have three stable resonance structures. So the fourth one is not going to be stable for those two reasons.
So on the test, if you asked to give us the resonance structure,
I would want you, maybe if you wrote it, what I would expect you to do is I would expect you to if you wrote it, to say it's not stable. I might even ask you to write, if I asked you to do this, I would say write all the stable resonance structures. So in this case, we got three. Okay, does that make sense? So we just have three. Now what about adding to A or C? How many resonance structures did you get? Two stable ones. So adding the E plus to A would give me the H and the E here, and the positive charge there. Okay, so there's one stable resonance structure. Then what would I do? I'm going to take this pair of electrons and move it here to form the second resonance structure, right? And now how about the third one? Take this pair of electrons and go here. So we get 3, are all 3 stable? You can answer anytime. Yes.
The one with the positive.
So having a positive charge on the nitrogen is not going to be as stable as the others. So this one's going to be less stable. Do we agree with that? So really, how many stable resonance structures do we have? We just have 2. So adding the electrophile to A, and then what happens if you add the electrophile to C? You get the same series, so you only get 2 stable. So adding the electrophile to A or C, you're only going to get 2 stable resonance structures, whereas if you add the electrophile to B, you're going to get 3. And so in doing this, what we're saying is that the more resonance structures, the more stable the intermediate. That goes back to resonance theory from day 1. So having 3 resonance structures is a more stable intermediate than having 2. The major product comes from the more stable intermediate. And so in this case, when I do this reaction, I'm going to end up adding the electrophile to carbon B. That's where I'm going to do my substitution. And when we started talking about electrophilic aromatic substitution, even though I did that really quickly, that's kind of what we were doing, except I never made you write out all the resonance structures. Okay, so if I said if I gave you that reaction, the major product would be adding, first of all, what's my electrophile? CH3 plus. And where would it go? It would go meta to the nitrogen. So it would go, that would be the major product. Okay. So that's how we have to determine for these heterocycles where the electrophile would go. And at this point, it doesn't matter whether the heterocycle had in a 6-membered ring, whether it's a nitrogen, oxygen, or sulfur, it would go meta. It would add the CH3 meta, add any nucleophile, or sorry, any electrophile meta to the heteroatom.
For adding these, I can only get one.
There's one. Now I can take this pair of electrons and move it like that. Well, let's continue on. So, I can still do this, right? As the same one, which is the same. So if these are A, B, and C, let's deal with the first issue and then I'll come back to that. Any of these unstable? B. So B is unstable. Now, when you say same, when you say A is the same as C, no. They may have the same energy, but they are not the same structure. Because remember, in writing resonance structures, what are you allowed to do? You're only allowed to move electrons. So when we look at this ring, it's as if this carbon and this carbon are like different than this carbon and this carbon. You can't take the molecule and you can't rotate it. You can't move any atom. You can only move electrons. So all 6 of those, well, all 5 of the carbons in the ring and the nitrogen are unique atoms. And so A and C, I will give you that they have the same energy, but they are not the same resonance structure. Because you're not allowed to move atoms, you're not allowed to rotate, you're not allowed to flip, you're not allowed to do any of that. So A and C may be the same energy, but they are not the same structure. So therefore, this has 2 resonance structures, and unfortunately 2 does not beat 3. So adding to B is still a more stable one. Okay, does that make sense? So where did the electrophile end up adding in the 5-membered ring, which is called pyrrole? A gives the most number of resonance structures. How many of them are stable though? So it's got 2 stable ones if you add it to A. And how many for B? When you add to B, you get 2 but only 1 stable. Did everybody else find that? So if you add to B, you get 2 stable resonance structures. If you add to A, you get 2 stable resonance structures. If you add to B, you get only really 1 that's stable. So then that would be the major product of that reaction. So that was almost the end of amines. And I say almost the end of amines because there's 2 other reactions that we need to talk about that have Well, we're going to have a sense of deja vu here when we do these reactions. But they're called Cope and Hoffman elimination. So we'll talk about Hoffman elimination because the Hoffman name has come up in E2 reactions, or E1 and E2 reactions. So if we just go back for a quick review here, and we're just going to do cyclohexanes. If I take this alcohol and I treat it with H2SO4 and heat, where's the double bond going to form in that molecule? Between A and B, B and C, or C and D? Where's the double bond going to form? Give me a letter combination. B and C? Do we agree? No, and I didn't say no rearrangement. But without rearrangement, we're going to get B and C as the alkene. Okay. And why is that? Because that alkene is the most, making the alkene the most stable, and so that's called Zaitsev's rule. So if we formed the other product, that was oftentimes, if we were to form this product, if this is the Zaitsev product, then this would be called the Hoffman product. And I always forget there's one F and two N's. And it's Hoffman, not Hofmann. I had to Google that to, because there's also a Hofmann out there. So that would be called the Hoffman product. And the problem when we start talking about E1 and E2 reactions is we can say, oh, well, that's the Hoffman product, so we'll have to wait until Organic 2 to talk about where the Hoffman name comes from in the Hoffman elimination reaction. And, it's just like wait till next year. It's next year, right? Now we're in Organic 2, so now we got to talk about Hoffman. Now the Hoffman reaction is nothing, has nothing really to do with E1 and E2 per se. In Hoffman elimination, here is what I would do. I'll use the same molecule. What I'm going to do is I'm going to take and I'm going to put a nitrogen there. I'm going to put an NH2 molecule. And so what I need to do is I need to alkylate that nitrogen so that it becomes an NR3+. So I'm going to what's called completely or exhaustively alkylate that nitrogen. And how did we do that yesterday? What we did yesterday was we added an alkyl halide to it. What kind of reaction occurred? SN2. And so I would now add an alkyl group, but then the nitrogen became positively charged. And then in order to add the next alkyl group, what do I have to do here? I have to add something like hydroxide. I have to add hydroxide to this in order to deprotonate the ammonium to then make now a neutral amine. So every time I alkylate, I have to add hydroxide in order to make the neutral amine so that I can do the next alkylation. So what I'm going to do is I'm going to simplify that, and basically I'm going to say, you know what, I want to add 2 more alkyl groups, and I'm going to do that with hydroxide so that in the end I'm going to have this nitrogen have 3 total alkyl groups off of it, which is going to make it have a positive charge. And so what I can do now is, we wouldn't necessarily think a nitrogen with a positive charge is a good leaving group, but it is. And it's a good leaving group so that if I take my hydroxide, not exactly the most powerful base, but if I took my hydroxide and I applied heat to it, I could get the hydroxide to come in, grab A. Okay, we got to go back to E1, E2 here. We've got our alpha carbon, we got our beta carbon. The OH minus would come in and grab a beta carbon. The pair of electrons would move down here, and then that pair of electrons would move to the nitrogen as the nitrogen plus group leaves. As the ammonia group leaves, and actually leave as a tertiary amine, so that what I would end up doing is forming the double bond. I would end up with the amine, since it's in basic solution. And we're going to classify this reaction as being E2. Now, Hofmann elimination always gives you the least substituted product. And at this point you might say, well, why is that? Because if I consider hydroxide to be a small base, wouldn't it much rather pull off this beta hydrogen that's attached to the ring? Wouldn't it rather pull off that hydrogen and form the most substituted product? And the answer is it would, accept this as Hofmann elimination. So the rules for Hofmann elimination actually change. First of all, being E2, the H and the leaving group have to be anti-periplanar. Okay. So those two groups still have to be anti-periplanar. But the way this works is that this reaction will give a major product from losing the hydrogen, the beta hydrogens, or losing beta hydrogens off of the carbon that is most, or is least substituted, that has the most beta hydrogens. So the way this works is any of these 3 beta hydrogens could go into an anti-periplanar geometry and be pulled off with hydroxide. Whereas over here I only have 1 hydrogen, and I would have to put that anti-periplanar in order to get it to be removed. And so in this case, the hydroxide is going to remove those 3, can remove any of those 3, which is going to give me that as the major product. So it's not about the stability of the product, it's more or less about the transition state energy in terms of being able to find more hydrogens that can be anti-periplanar off the CH3 versus the CH. So that's the reason for the Hofmann to eliminate this way, or the ammonium to eliminate this way. So the ammonium group still has to be anti-periplanar. You still have to have the hydrogen and the leaving group be anti-periplanar. But it's going to form the least substituted double bond. Okay. So those are the rules for the Hoffman elimination, as we find experimentally. Okay. So typically how we do Hoffman elimination is this. Let's talk about let's do a real molecule here. So let's say I treated this molecule and I want to do Hoffman elimination on it. My first step would be to add 3 alkyl halides under basic conditions. And so the first thing I have to do is I've got to completely alkylate, bless you, my nitrogen. So I'm going to change that nitrogen into now an NR3 plus group so that it can leave. So that's the first step you have to do is 3 alkyl halides with hydroxide. And then I'm going to, in the second step, I'm going to heat this. I'm going to use hydroxide and heat to do the Hoffman elimination. Now, oftentimes in the textbooks, what you'll actually see is this. Instead of them using hydroxide in both of these steps, you'll see something like 3 alkyl halides, silver oxide, and heat. That might be your reagents. And this is a pretty old school way of doing this reaction. The 3 alkyl halides make sense. That's to alkylate. What's silver oxide doing there? Well, if we go back to general chemistry, when you take silver oxide and you put it in water, what do you get? You get a silver ion and hydroxides, because the oxide is a strong base and will deprotonate the water. Except the problem here is silver oxide isn't very soluble in water, so the equilibrium arrow is going to be mostly to the left. But silver oxide will still produce some hydroxide. So what happens is as you alkylate, what happens is you form your HCl, and then that HCl reacts with the hydroxide that the silver oxide has produced. And once that hydroxide reacts with the HCl to form water and Cl minus, which of course, what does the Cl minus do? The Cl minus combines with the silver plus, because silver chloride is not soluble in water, so you end up forming a silver chloride precipitate. As you react hydroxide, what does the silver oxide do? The equilibrium by Le Chatelier's principle of removing hydroxide, the equilibrium shifts and makes more hydroxide. So when you use silver oxide, you're making enough hydroxide, you're making it as you go. So as it gets used up, you make more from the solubility equation. So that way you don't have to keep adding hydroxide, and you'll have just enough. So somebody came up with this idea of adding silver oxide. I mean, it's expensive, but I suppose if you get the silver chloride back, that's okay. And then take your silver oxide and make hydroxide as you go. So this, you'll see these sets of reagents as well. Does that kind of make sense? It's just a convenient way of making just enough hydroxide as you need it. And then at the end of the reaction, you just filter out the silver chloride, silver oxide. So now we're going to apply heat and hydroxide, the hydroxide that's present, and we're going to go ahead and do this reaction. Now, what's our major product of this reaction going to be? What's the first thing I've got to do? This is an E2 reaction. Anti-periplanar geometry. Cameron? Nope, even before that. Even before that. It's an E reaction, so what should I label? My alpha and beta carbons, and find the beta hydrogens that can be lost. That's the first step. So where's my alpha carbon? Here. How many beta hydrogens do I have? Well, how many beta carbons do I have? Got one beta carbon there and another beta carbon there. So I have 2 beta carbons. We'll call this beta carbon A and beta carbon B. What's the major product? Which beta hydrogen am I going to lose? Hydrogens from beta carbon A or beta carbon B to form the major product? B. So I'm going to lose hydrogens from beta carbon B to make my major product. The major product being the one that comes from the carbon with the beta carbon with the most hydrogen. So writing that product is going to look like this. Here's my CH2 group with my H over here. I'm going to have nothing happens to the stereochemistry, so the major product of this reaction is going to have a CH3 here. And then down here it's going to have the ethyl group. Okay, so that's the major product of the reaction. So all I did was the hydroxide, if I want to change, I can change this and make it a CH2 with an H here. The hydroxide comes in, grabs that hydrogen. This pair of electrons moves here, and then the ammonium leaves. So I end up forming the double bond to the CH2. So that's the major product of that reaction. That one, piece of cake. Well, that one, less steps than the next product. Okay, so that's the major product because that's what Hofmann elimination does. The second product, which is not major, is to now remove that hydrogen, to remove that beta hydrogen. Okay, so what do I have to do there? This is what you wanted to start with a minute ago. So this reaction has to be anti-periplanar, right? Right. So what do I have to do with that hydrogen that's in the box? I've got to make it anti-periplanar to the leaving group. So how am I going to do that? I'm going to rotate it to the methyl group down where the ethyl group was, and then the ethyl group back to the hydrogen. Because what I need to do is I need to have this in this geometry where the NR3 plus group and the hydrogen are now anti-periplanar. So the methyl group came down here, the ethyl group came up here or came there, and then the other two, the hydrogen is here and the methyl group is there. So now what happens with, now my little bit of hydroxide that's formed comes in, grabs the hydrogen, the pair of electrons goes there, and the nitrogen gets kicked off. So the second product in this reaction, the question now is, are the two methyl groups going to be cis, or are the two methyl groups going to be trans in that product? And so the groups that are bold are going to end up on the same side of the double bond, the methyl and the hydrogen. And then over here, the ethyl and the methyl group are going to be also cis because they're now in the trans. So this is the only stereochemistry of the double bond that's formed in this reaction. The other product cannot be formed because the hydrogen has to be anti-periplanar, and that leads to this product only. So the double bond where the two methyls are cis is not formed in this reaction. Only the ethyl and the methyl group being cis is formed. So we've done these kinds of problems before. Whether it was in Organic 1 or whether it was in this class is what I'm kind of unsure about. But this would be what you would have to do if you did an E2 reaction on an acyclic compound. So you've got to put the beta hydrogen in the anti-periplanar geometry. Now you might say, but we didn't worry about that up here. We didn't worry about that. That's because there were 3 hydrogens and any of them could be rotated to become anti-periplanar. There was no stereochemistry. But in this case, forming the Z double bond, right? Z because ethyl and the methyl have high priorities. Ethyl over this methyl and methyl over this hydrogen. So these are my 2 high priority groups. They're together. That's Z. So the geometry has to be anti-periplanar on the second product. The first product, there's no stereochemistry. It's easy to draw. It's the second product that becomes a little bit more difficult. Does that kind of make sense? So it's like E2, whether I'm doing an E2 with maybe like a tertiary oxide or with an NH2 minus, I've got to be careful to make sure that if I give you the stereochemistry of an acyclic product, that's where you have to put it into the proper sawhorse projection, which is what these are, sawhorse projections. So we'll do a problem here after I introduce the next. So this is Hofmann elimination. Hofmann, you're going to form the least substituted double bond, and it has to go through an anti-periplanar geometry. Now, there's a second elimination, as there always is, where you still get the least substituted double bond, but instead of going through the anti-periplanar geometry, you go through what's called a syn or periplanar geometry, where the hydrogen and the leaving group are in the same plane and on the same side. So that is called Cope elimination. And so Cope elimination has those different characteristics, and it has a different reaction to it. So let's see, if I can remember the molecule I just drew, I can write it again. So you know what, let's just put the hydrogen here. I think the ethyl group was here, the methyl group was here, doesn't matter, it's a new problem. Then I'll put my N group, my NH2 group here, and what do I have? I'll have a hydrogen, and then back here I'll have a methyl group. Okay, so if I started with this molecule and I want to do Cope elimination, I have to adjust the reactions to get there. And in this case, what I'm going to do is, number one, I'm going to get out of this stupid slideshow mode because it's driving me up the wall. And so if we go with the Cope elimination here, I'm going to react this now with two equivalents of alkyl halide, and then we'll just go ahead and use hydroxide. And so now I'm going to alkylate the nitrogen group twice, because Cope involves a different species altogether. So I'm still going to have my ethyls and methyls. I'm still going to have my hydrogen, my methyl. But now what I've done is now I've dialkylated, or I've basically got a tertiary amine. So I only put two alkyl groups on. Now, if we use a mild oxidizer on this nitrogen, we're going to transform it into a new kind of a species. So first of all, my favorite mild oxidizer is our peroxy acid. And what happens when an amine reacts with a peroxy acid? What it ends up doing is it ends up forming what's called an amine oxide. And so this is an amine called an amine oxide. I like the peroxy acid because it's consistent kind of with what peroxy acids do. Right? What do peroxy acids do? They add an oxygen to something. Okay. They add an oxygen to make an epoxide. They add an oxygen to make a lactone or an ester. In this case, they add an oxygen to the nitrogen, and they make this amine oxide. And now here is the issue with the amine oxide. The amine oxide will undergo, with a little bit of heat, will undergo the elimination in this fashion. So what I'm going to do here is I'm going to jump ahead, because I'm just going to write what the amine oxide does here, and then we'll go back to that problem. So here's what the amine oxide does. The amine oxide, in order to remove so there's my alpha carbon, here's my beta carbon. In order for the amine oxide to remove the beta hydrogen, it has to be cis, or syn, S-Y-N, and it has to be periplanar to the beta hydrogen so that it can form a 5-membered ring transition state. So this O- is going to grab the beta hydrogen, the pair of electrons is going to move there, and then the pair of electrons is going to go to the nitrogen. And this nitrogen has a plus charge, so it's going to be happy to get the pair of electrons. And so this has to be a syn periplanar transition state, as opposed to our anti-periplanar geometry from the last one. And so what we end up doing then is forming the double bond, and what is then called a hydroxyl amine. Some of these functional groups, like amines, and we didn't talk much about sulfur compounds, they have their own series of compounds that you can make with their own terminologies. And so amine oxides and hydroxylamines are sort of subspecies of amines. And so the amine oxide will then basically form the double bond, but it has to be syn and it has to be periplanar. The rules are the same as they were for the Hoffman elimination. So the Cope elimination always forms as the major product. You're going to get the least substituted alkene as your major product. So if you took a molecule and you did Hoffman and Cope on it, your major product would be the same in both cases. It's going to be the second major product that's going to be different, because now I have to put the amine group syn periplanar as opposed to in Hoffman anti-periplanar. And so in this case, if I did this reaction with the same molecule that I did the first reaction, the Hoffman, the two methyl groups, instead of being trans, would now be cis. So I would get the exact opposite product as the second product, not as the major product. Okay? So let me go back. Let's orient this molecule to undergo Cope elimination. And how am I going to do that? I'm going to have to put that into this U shape. And when I say U shape, I'm focusing on the bonds that are in the plane of the screen, or the plane of the paper. Right? There's sort of the S shape, and then there's the U shape. In this S shape, where the bonds in the plane are kind of in that S shape, that is when they are staggered, right? That's going to be a staggered conformation. If I look down this end of the molecule, I'm going to get a staggered Newman. Whereas if it's in the U shape, if I'm over here looking down that bond, it's going to be eclipsed. And so syn periplanar has to be eclipsed. So anything going to change here? No. The left molecule is going to stay the same. I'm going to have to rotate. I'm going to have to rotate now the methyl group up, or the N group up, and rotate them around that way so that the nitrogen then is going to be here with its R group there, its R group there, and its O minus group there. And then that's going to force what? So I'm going to basically make a 180-degree rotation. So if the hydrogen is up coming towards me, in the end the hydrogen's going to be down pointing away from me, and the methyl group's going to be not back but forward. So now I have the molecule in the correct geometry to now make both products. So I'm gonna rewrite this. So H N O minus with two R groups on it. The two methyl groups are pointing towards me. The ethyl group is away, and the hydrogen is there. I'm going to take this methyl group now, and I'm going to make it a CH2 with an H coming off of it. And why am I doing that? Because now to write the major products of this reaction, I go back to basics. A, alpha carbon, beta carbon, beta carbon. Beta carbon A, beta carbon B. Which one am I going to lose the hydrogen from to form the major product? Beta carbon B. So then my major product is going to, the carbon on the right's not going to change stereochemistry. And then I'm going to end up with my double bond to my CH2 and my hydrogen there. So that is, again, the major product, the same product as I got in Hoffman. But now the second product's going to be different. And so now when I form the second product and have this pair of electrons grab the hydrogen, pair of electrons moves there, nitrogen, what am I going to end up doing? All the groups that are on the dashed wedges will be cis. The groups that are on the bold wedges will be cis. And so in this case, the two methyl group, hold on. That makes no sense. The two methyl groups on the bold wedges will be cis. So the two methyl groups now are cis in that product. So Cope should give the exact opposite of Hoffman for the second product. The first product, the major product, will always be the same, whether you do Cope or Hoffman. So it's the second product that's going to be an issue. And when I give you the stereochemistry, that's why I'm giving you the stereochemistry. So this is kind of what we did with E2 of acyclic compounds. It is a minor product, but it's the minor second product. The major products are the same in both sets of reactions. It's the minor products that are different. And in order to get the minor product, what you need to do is you need to manipulate the sawhorse projection. In this case, we get the amine. In this case, we have to make the amine oxide and then do the reaction with heat, and then we get the hydroxylamine as the other product. So this would be the other product. In both cases, it would be the alkene plus the hydroxylamine. And we usually don't mess with the hydroxylamine. We don't show it because I'm more interested in where the double bond is. And now I'm interested in not only where the double bond is, but what the stereochemistry is. So one's anti, one's syn. Both periplanar. Does that kind of make sense? Okay. We'll come back and I'll give you a problem and we can do that before we go. Although I'd probably be more effective if I gave you a problem as a take-home quiz problem. Yeah, it would be more effective. We should probably do one in class before we do that. So that's the end of amines. Now remember, we talked about amines when we did when we were adding an NH2 to the ring and we were doing diazonium salts. So those topics are actually in chapter 23. And again, I'm against my better judgment here. I'm kind of leaving it up to you to go through the top hat problems. So hopefully I will take a look at those probably tomorrow and I'll see where everybody's at. But hopefully like chapter 13, everybody's done. If you haven't done chapter 13, you probably haven't done 14, 15, all the way through to now we're going to start 24. Again, I don't believe the answers to those problems are on Chegg. Not that it matters because you're getting participation points, you're not getting credit points. But if you just are randomly choosing answers, that is defeating the purpose of the problems. Okay. So next week I'll be going through and writing down the final scores. Like I said, the last time I left that to the students, they had like one weekend where they were doing like all 12 chapters. But they had the ability to get the answers from Chegg, which is why I dropped that company. No, not if you wait until the end and you pay your $15 for 1 month and then you use it a lot. $15 a month? That's only $15. If you have it for the entire academic year, then that's $15 a month times 9 months. Well, then you should just be doing the problems in the book and the problems that I give you, and you don't have to worry about Chegg. Okay. Next functional group. We have roughly three functional groups left. which is good because we have basically today, Thursday, half of Monday and Tuesday. So we're just about there. Carboxylic acids. So, there is a carboxylic acid. Naming carboxylic acids, there are common names to carboxylic acids, and there are common names to dicarboxylic acids. I'm going to leave that for the book. The difference between, let's say, formic acid, which is the one carbon acid, acetic acid, propionic acid, butyric acid, which is, all these names come from, well, except propionic acid. Formic acid you get by squishing ants. That's where it came from. That's where the form sort of originates. Acetic acid obviously is vinegar. Butyric acid comes from basically being the smell of rancid butter. I took all the butyric acid out of the esters that we're doing this summer in lab. I took them out in the spring as well because they reek and they drive me up the wall. So I took everything that had a butyric acid out, and it's never going back in as far as I'm concerned. I think we actually might have taken them out for Dr. Kwan as well, though I don't think he was aware of that. So that we didn't have the lab smelling like basically a rancid butter. A rancid baby diaper is another one. And that goes to Valeric and a bunch of others. So these have actually common names that you hear, but that's as much as I'm going to get into that. We have to start with what ways do we know to make carboxylic acids right now? So let's see how many ways I can remember to make carboxylic acids that we've talked about. There's one. There's two. There's three. Are there any others? Oh yeah, there's tons of others. I should have you generate this list instead, but we don't have all day. Well, they're not exactly ripping out of my head right now, so there'll probably be a little bit of delay between where they are in my head and where they are in your head. Let's start with those. Anybody want to give me a reagent for any of these? Kayla? Katie? Mg, CO2, and then there's always a then H plus step. Grignard. And I just put the benzene ring on there hoping that would trigger something, since it's only Monday that you may or may not have had to do that. O3, and then what with O3? Take a guess.
What is R2S?
Okay, it's not R2S, so it's the other one. H2O2. That's ozonolysis, right? Ozonolysis cleaves the double bond, and if you initially make an aldehyde, when you cleave it and replace the two C double bond C's with the CO double bond O, the H2O2 oxidizes the aldehyde to a carboxylic acid. Which means H2O2 would fit where? It would fit down here. So H2O2 could be used to make an aldehyde into a carboxylic acid. So it would fit the fourth one. Okay? Still plenty of reactions to choose from. So second to last one would be CaMNO4 or what kind of oxidizers CaMNO4? Strong. So any of the strong oxidizers, any chromium 6s, any strong oxidizer would take a primary alcohol all the way to the carboxylic acid. Actually, it's easier to remember the oxidizers that stop at the aldehyde for a primary alcohol, and that's like PCC, and then somewhere in there I think Swern and Desmartin were also thrown in one of the later chapters. But PCC is the one I know we did in class. Okay, so strong oxidizers will take primary alcohols to carboxylic acids. Is that also true for the last step? For the last one? H2O2, any strong oxidizers? Except there's two more reactions that I can use that are specific for aldehydes going to carboxylic acids. For the last one. They're specific for aldehydes, and they give colorful products. So the copper 2 plus on hydroxide, which is called, starts with B, that's Benedict's. And then, what's the other one? Silver, hydroxide, and ammonia, which is called Tollens. So the Tollens and Benedict's also can be used to make carboxylic acids. They're specific for aldehydes, or any of the strong oxidizers will take an aldehyde to a carboxylic acid. Which leaves one left. How do we take a nitrile to a carboxylic acid? We do hydrolysis, so H plus H2O. So, oh, we have more. We have 2 more that I forgot about. For the nitrile, yeah. H3O plus is the same as H plus and H2O. And heat, sure. It's same reagent. Okay, here's 2 I forgot. Give me one. I can do it in 1 step. 1 step. That is an alkyl benzene being oxidized. Sorry. And so this, and the second one, I'm actually going to cleave. I'm going to cleave the carbon-carbon triple bond. So how would I do that? I'm going to have to use a fairly harsh reagent because carbon-carbon triple bond is more difficult to cleave than a double bond. So actually ozone's out. No, that's the other product. That's the other product the way I've written it. That will reduce. I want an oxidizer. So if you're like totally clueless as to what you should add, this probably isn't going to work if you're totally clueless. But if you're just kind of stuck, I would look at this and I would say, okay, I'm cleaving and I'm adding oxygen, so I'm doing an oxidative cleavage. You might say ozone. I would say no, because triple bonds are harder to break than double bonds. So I need to cleave and I need to take it up a notch. I need a harsher reagent. How about CamNO4 and acid and heat? I need all 3 of those things. So that, I will not guarantee that's an exhaustive list, but that's the way we've made carboxylic acid so far this year. So now we need new reactions of carboxylic acids. And we'll start with a review of old reactions. All right, so we will start at, so take a break, 10:35, we'll start back up again, and I will give you a list of reactions of carboxylic acids that we already know. And we'll start with that. Okay. So, let's start with reactions we know of carboxylic acids. Here are 3 that I think we've encountered recently. No, 2 of them recently. Anybody have any suggestions? You want to fill in a box? Kaylee? Or PCl3. Okay, the low-hanging fruit box is gone. That's why you got to be aggressive and answer first. I would think somebody in lab would be able to fill in the first blocks. How about what kind of reaction is that first? What kind of esterification? So this is Fischer esterification. So I'm going to make an ester out of the carboxylic acid part and the alcohol part, and then we would make water. So Fischer esterification, carboxylic acid plus alcohol makes ester. Okay, we've got 2 boxes left. In that case, it would be plus HCl. Okay, so if you take an acid chloride and react it with an alcohol, you make a carboxylic acid, or you make an ester. And then carboxylic acid plus lithium aluminum hydride. What kind of alcohol? Reduces it down to a primary alcohol, yes. And so I think these reactions have been, I know the esterification reactions were back in the organometallic with the Heck and the Suzuki, all that couplings, because there were reactions of phenols, and one of the reactions of phenols is Fischer esterification. So those are reactions we already know. The carboxylic acid chloride is its own carboxylic acid derivative, and so it's going to be the first one we talk about, either today or tomorrow. So let's talk about carboxylic acid reactions that we may or may not know. So let's take the carboxylic acid and just by itself. Now I can convert the carboxylic acid to an acid chloride and do all those reactions like I said. We'll do that at the end here, or most likely we'll do that tomorrow. But just the carboxylic acid itself. I can do esterification, Fischer esterification, alcohol, carboxylic acid, sulfuric acid as a catalyst. I can react acid chloride, alcohol. And so let me just, there's some comment I should probably make on those two reactions and why, well, and the, I don't know, pros and cons of each. So traditional Fischer esterification, simple to do, okay, it takes a while. Right, it took us an hour and a half of reflux in order to get the equilibrium to set, plus then the days it's been sitting in a bottle on the table waiting to be distilled today. So it takes a while to get to the equilibrium. If I'm going to push the equilibrium all the way to the right, I need to use excess of one of these two reagents. So this is actually a case where I have to use Le Chatelier. So typically if I want to force this reaction to go to the right, I use excess carboxylic acid, and that will help push the equilibrium to form the ester in the highest percent yield possible. Why do I use carboxylic acid in excess and not alcohol? Because after I'm done with this reaction, I can take the excess carboxylic acid, I can react it with bicarbonate. So in other words, I can do an extraction, I can add bicarbonate to it, and I will deprotonate the carboxylic acid excess into carboxylate, that being ionic. It's going to go into the aqueous layer, and so basically by doing a bicarbonate wash, I can remove any excess carboxylic acid, and then I can go ahead and just dry and distill my ester for purification. Well, that's what we're doing this afternoon. So that's why you use that. If you use excess alcohol, how do you get rid of the alcohol? You got to be fortunate enough maybe to distill the carboxylate or the ester from the alcohol. It's easier just to use excess carboxylic acid. So the other issue with this is that equilibrium. We've got to overcome the equilibrium somehow. And depending on how sterically hindered your alcohol is, it may or may not work well. So Fischer esterification, its major issue is the equilibrium and how to overcome that. But it works pretty well. You just add the two things together, add sulfuric acid, and let the reaction go. If you want to overcome the equilibrium issue, that's when we can take our alcohol, use SOCl2 to convert it to the acid chloride, and then react that directly with take our carboxylic acid, convert it to an acid chloride, react with alcohol, and there's no equilibrium. That goes 100% to form the ester. And so there's no issues. There's no issue. There's an issue of 2 steps versus 1. But if you want to overcome the equilibrium, you go to an acid you convert the carboxylic acid to an acid chloride and then react. So that's another method to make the esters. And the new one would be to react the carboxylic acid with what's called diazomethane. And so this would be one of the resonance structures for diazomethane. Now what happens here is, again, when did we see the sort of the two nitrogens bonded together is going to make a pretty decent leaving group. The problem is it's a gas molecule. I think it was just yesterday, wasn't it? So we've got a decent leaving group here. And what we want to do then is the alcohol will come in and basically add to the carbon. There'll be a rearrangement. You'll end up making N2, and you will methylate your carboxylic acid to make an ester. So this is diazomethane. Diazomethane works specifically to make methyl esters. How many times do you need to make specifically just a methyl ester? Yeah, there's one class of compounds that if you take a fatty acid, which we also kind of talked about yesterday, fatty acids with long chains, and then the carboxylic acid part. If you take a fatty acid and you want to determine the compositions of different fatty acids in a mixture, they do not GC well because they're carboxylic acids. But if they're esters, they have a lower boiling point, so they go through the GC. And actually, columns have been made specifically to analyze fatty acid compositions. And so what you can do is, if you have a fatty acid, you can use diazomethane to make the methyl fatty acid, which is actually called a FAME, a fatty acid methyl ester. And then you can do your analysis of all the different fatty acids in your molecule. And with interest in biodiesel recently, we do not have a biodiesel plant on campus. We do not take the vegetable oil from the cafeteria and make biodiesel and run our vans and our construction equipment on it. Somebody asked me about that one time. I said, no, not doing that. Loyola Chicago actually does that. They take their vegetable oil and they basically make biodiesel, and then they make soap and stuff out of it. But we're not going that route. There's a lot of paperwork involved there and a lot of money to set this up that we don't have. So we're not going to be doing that. But there were people that do that. So when biodiesel, gas prices are relatively inexpensive right now. Relatively. They could be worse. Whenever gas prices go up, we talk about alternative energy, and biodiesel always comes into play. Right? We go to Wendy's and hijack all of their vegetable oil from their big tank. Although the tank says, do not touch this, because apparently there's companies that come around and take it. And it's a competitive business, the vegetable oil recycling market. But if you wanted to, this is one of the reactions you could use. Issue here is diazomethane, embedded gas molecule, got to handle with care. You actually have to generate the diazomethane as you react it. So it's not like I go down to the stockroom and say, hey, give me a bottle of diazomethane. You can't. You have to have special glassware to make it. So It works to make fatty acid methyl esters. It works to make any methyl ester. It's not. It's an old school method, and is probably not used all that much. For biodiesel, the way we would do this is we would react carboxylic acid with methanol. And then we have to make sure that the methanol content of the fuel is low enough where it doesn't blow up the engine. Because methanol will combust completely differently than biodiesel will. So that comes around. I think people have actually had vegetable oil cars they could run on just pure vegetable oil. I've never seen one, I've just heard about it. So that's esterification. What else can I do? I can react carboxylic acid with amines. Now, the product of this reaction, we'll just go. I won't even mess around with that. Here is the product of that reaction. It's basically what kind of reaction? This is an SN1, SN2, E1, E2? No. Oxidation, reduction? No. Acid base? Yes. Because I'm reacting a carboxylic acid with an amine that is a base. Okay. Right now, you may not have been tempted to add the nitrogen to the carbonyl group. Or maybe you would have been, given that's what we did with aldehydes and ketones, but we don't. This is an acid-base reaction. And you make an ammonium carboxylate salt. And what good is this? Well, I'm going to take the liberty here of sort of talking about biochemistry. Given my biology background that I described, I think earlier this week, that's probably not a good idea, since you have infinitely more than I do. But then again, I might sandbag you a little bit. Usually I say I know this much and my fingers are really, really close together, but they are not touching. There is a little bit of gap there. So there is a little bit of knowledge. What is this? This. What functional groups does it have in it? An amine and a carboxylic acid. It's an amino acid. Right? And there's how many of those? 20 something? Low 20s. 22 give me 3 either way. I think it's 23, right? Good. That's a good way. At least 20. Then there's the non-naturally occurring ones. So you'll memorize those when you take biochemistry, or if you had to memorize them before, then why aren't you answering the question? I am. So this is an alpha amino acid. What happens when an alpha amino acid is dissolved in water? Well, it can transfer a proton from the carboxylic acid to the nitrogen. So a lot of times you will see the structure of an alpha amino acid looking like this, and then there are all these different points or all these different structures you can get. Like, does it look like this when it's in acidic or basic conditions? Does it look like this when it's in neutral conditions? So when you take biochemistry or you talk about amino acids, you're going to talk about different forms that exist when they're in basic or acidic solution. The reason is because they can start off like this, as ammonium carboxylate salts. Well, they're not really salts, they're just, that transfer of proton can occur. So this is relevant to amino acid chemistry. But I digress. The ammonium carboxylate is useful if you then heat it up. It will eliminate water, and it will allow you to form an amide. And so it will decompose when you heat it, and it allows you to make the amide. Okay. This is a very traditional, very old school, early 1900s method of making an amide from a carboxylic acid. My first graduate student did this. We were trying to do this reaction to make the amide. We were using ammonia, because we were using N15 enriched ammonia. And what we found was that we found an old paper, like 1920s, 30s, that said, hey, do this. And then we tried to use it with modern chemistry equipment like a hot plate. And after it failed, we're just like, why isn't this working? And then we're like, well, we have to think about what we would use back in the 1920s. And so what we would use back in the 1920s is a Bunsen burner. And so then when we used the Bunsen burner, it worked fine. We would just put in the round bottom and then heat the snot out of it with a Bunsen burner. And it worked. Fine line between heating and decomposing and burning. So it works. It's probably not the most sophisticated way. I might convert the carboxylic acid to an acid chloride and then react it with the amine. Why didn't we do that? Because acid chlorides are not stable in water, and we had this ammonium solution in water. So it works. But this is the step that you have to remember, because if I give you this scheme next Monday, you want to make sure you have the ammonium carboxylate and don't add the nitrogen to the carbonyl. Because statistically, at least one of you will do that next Monday, even though I tell you, don't do it. Okay? So you want to think that through. And this is like, well, we'll come back. We'll come back to something else that we tend to write the wrong product for. All right, so this is ammonium carboxylate. So this is called a condensation reaction because I produce water. So in top hat, this is called a condensation of an amine. With a carboxylic acid to make an amide, it's as simple as that. Okay, next. And this may just seem like one reaction after another because it's one reaction after another. All right, next, carboxylic acid. What is a new reaction we can do? And I didn't do the mechanism of the decomposition because it doesn't matter. You're heating it, you're losing water. It's as far as we need to go. Reductions of carboxylic acids. I think I got myself in trouble yesterday by the magic step that I then bailed on. This is the magic step I was thinking of. All right, so I'm going to add lithium aluminum hydride to my carboxylic acid, and what am I going to make? A primary alcohol. You already established that. What's the mechanism? All right. What is lithium aluminum hydride a source of? H minus. How many H minuses do I have? Up to 4. All right, when I react my carboxylic acid with a hydride, what do I get? Be careful. What's the hydride going to do? What do you mean by attacking the oxygen? It's going to deprotonate the OH. That's going to deprotonate the OH. Why did I follow this reaction, or have this reaction follow the ammonium carboxylate? Is this the same thing? You're going to want to add the nucleophile to the carbonyl group, but with carboxylic acids, we have to be careful, because if that group is a base, it's deprotonating, not adding. So in this case, it's deprotonating. That's okay. I just used 1 H minus. How many more do I have left? 3. All right, now let me add my second H minus. What's it going to do? Now it can attack. Okay, so now I got 2 O minuses. Remember, my goal is I got to get rid of one of these O minuses. I have to get rid of one of them because I need to form a primary alcohol. There was a time when I invoked some sort of magic step to get there. I will not invoke that again, but I will go back to yesterday. Let's take a look at the aluminum H minus, or ALH4 minus. How many hydrogens has it lost at this point? 1 deprotonated, the second one added, so I'm down to what? An ALH2, and let's see, ALH3 would have been neutral because it lost an H minus, and then losing another H minus from ALH3. So we go to ALH3, which is neutral, minus 1 H minus, 1 minus the second H minus, takes me to ALH2 plus. So that is going to be the counterion for one of these 2 oxygens. So I'm going to have an ALH2 plus. Okay. This is the magic step. Except that aluminum, it's not going to want to stay this way, because aluminum and oxygen form a very tight bond. So instead what's going to happen is I'm going to actually bond the aluminum to the oxygen. And we could go back to general chemistry and remember the fact that, well, maybe not remember, but we know metals form oxides on their surfaces. And aluminum easily forms an oxide. You can't go around and find pure aluminum out in the environment anywhere. It's always coated with oxide. right? And so that would be a tarnish, right? Your aluminum, your piece of aluminum isn't shiny aluminum, it's some sort of gray. If you have an aluminum door on your house, chances are, unless if it's not painted, it's going to be this gray color. And then you can say, well, I'm going to make it all shiny, and I go out there with a scrub brush and make it all shiny, and what happens? It turns gray again. Because aluminum reacts with the oxygen in the air very easily. If you want to weld aluminum, two pieces of aluminum together, you got to bathe it in nitrogen gas or argon gas, because if the oxygen gets in there, you can't have bare aluminum being welded together without protection from oxygen. I know I'm sitting here with shiny aluminum here, but that has a coating on it that's keeping the oxygen out. And it's not forming a lot of gray aluminum oxide. And if it was, then I would be drinking aluminum, because on the inside of the cup, the acidic nature of the soda would destroy the aluminum. Right? If you want to do that, what do? You get some acid, dump this thing in acid, and it'll end up being this like plastic inside. You can actually see the coating that's on the inside of the can, because the aluminum will be reacted with the acid at base. I won't tell you how to do that, but you can YouTube. There's plenty of videos where people have done that. So if you're in doubt that there's a coating on the inside that's protecting the aluminum from the soda, it's there, and that's how you get at it. But I digress. So aluminum is very reactive. It will form a bond. I won't say a covalent bond, but it'll form a really strong bond with oxygen. Okay, what happens next? I still got two H minuses. So how about I take this H minus and have it attack this carbon, and then have the whole aluminum group leave. And so that's what happens. So I end up now with two H's being added to the carbon. The Al kind of double bonded to the oxygen, which I'm going to put in quotes because it's probably not correct, but the aluminum group leaves. And so now I end up with a primary alcohol, alkoxide. And so now I'm done. So then I'm just going to add H plus to this, and I'm going to form the primary alcohol. So this is one of the reactions where the aluminum plays a role in getting the second oxygen to leave so that we can make a primary alcohol. So this would be the mechanism of that. Am I going to ask you this mechanism? No, but this is how the mechanism works. There are plenty other mechanisms that I can ask you as we go through this. Okay, so that's the mechanism of reducing a carboxylic acid to a primary alcohol. And that's going to be our primary method that we're going to use. Here's my next carboxylic acid reaction. I can react carboxylic acid with two Grignards, or this could be two CH3 minus Li pluses. What's going to happen? What's the first step of this mechanism? The CH3 attacks the carbonyl. It deprotonates the OH. CH3 minus deprotonates the carboxylic acid. It's okay? Well, I mean, this was the third, basically the third of these reactions that do deprotonation first. So hopefully if there's a fourth and a fifth or a sixth, like next week. But it's what I was saying, it's okay. There's another CH3 minus I've got. So now what's that CH3 minus going to do? Now it's going to attack the carbonyl. So basically the first CH3 minus is the deprotonate, it's kind of throwing it away. And then the second one's going to attack the carbonyl, just like the second H minus attacked the carbonyl. So now I'm going to end up with this. So I still have my two O minuses. Okay, that's great. Can I do anything? I can't because I don't have the aluminum. The only reason I was able to get rid of one of the oxygens last time was that I had the aluminum that could bond to the O minus. I don't have anything else. So this molecule's stuck. So it hangs out waiting for what? Our then H plus H2O step. And our then H plus H2O step protonates both of those O minuses to form this. And what is that? It's a hydrate. Are hydrates stable? Period. Are hydrates stable? May your answer could be, well, not unless they're special. Is this one special? Nothing special about this one. It's not formaldehyde. It doesn't have three halogens attached to the alpha carbon next to the carbonyl. It's just a run-of-the-mill hydrate. Is it stable? Nah. So what's it going to go back to? How do we make a hydrate? We reacted water and acid as the catalyst. What did we react with water? What carbonyl functional groups chapter was that in? It was in the aldehydes and ketones chapter. So what did I make this hydrate out of? What did I make this hydrate out of? Already got that. I'm waiting for the third thing, which is either an aldehyde or a ketone. Try again. Ketone. What specific ketone? But it has two things attached to it. Give me one of those two things. I'll give you one R group. What's the other group? Where did that come from? Here's my carbon with my two OHs attached to it. The fact that it has two OHs attached to it means this molecule is a hydrate. What are the other two groups? Here, we'll highlight them. What are the other... That's not my highlighter. What are the other two groups that are attached to the carbon? Where did they come from? They came from the ketone. So, you thought you were done with hydrates and maybe acetals and amides and imines and enamines, which we took care of the other day. They're still in play for the next test. As we add organometallic reagents to our carboxylic acids and our carboxylic acid derivatives, guess what we're going to be making? Amines, hydrates, maybe even an acetal here and there. And what's going to happen to them? They're going to go all the way back to ketones and aldehydes. So is this a mechanism I could ask you? Yes. But I wouldn't stop here at what's in the box. I would say, go all the way back to the beginning. No, I don't have to do that, but I feel it's my professional obligation to ask that question. And you know what? It's not that hard. Because all I got to do is add H plus to one of the OHs. And then what's going to happen? A water molecule is going to leave. And then what's going to happen next? Going to lose an H plus and reform the carbonyl. So, this is just a precursor of us doing this like another 4 times. So, if you need a refresher, get a refresher. Okay, tomorrow we'll talk about carboxylic acid. We'll mop up a couple things here, which we're actually going to be moving into chapter 25 really quickly. So we almost finished chapter 24 today. What? Oh, everybody did the nitrogen. Oh, I got 2 things for you. I got 2 things for you. Number 1, have your exams. Number 2, related to the exams, I have some additional problems that will be due on Friday. I know we don't have class on Friday, but you can take a picture of it and email it to me on your cell phone, and I will grade it and send it back to you. What are these problems that I'm giving you? I'm giving you extra problems from the exam. One of which is I screwed up one problem. So I'm going to ask you to take a benzene ring and fill in these boxes. Because what I forgot a couple of boxes that would have gotten you to the compound that you need. So the hint I'll give you is there's an epoxide somewhere in one of these boxes. And you need to get to the epoxide. The back one, nearly everybody chose the third synthesis problem, which I knew ahead of time would happen because I've been doing this a long time. The other two were a bit more challenging. And guess what these are? Those two problems. So they're worth 5 points each. So that's 10. Plus I think there's like another 9 points here. And whatever you get correct there, I will add on to your exam. If you don't need the extra points, you don't have to do it. If you need extra points, do it. And they'll be due on Friday, okay? I have not posted the answer key because I have to somehow separate the page with the syntheses out so that I don't give it to you, because that'll make things easy. All right, so these will be due on Friday. I will give you credit. Hopefully you tried the 5 and 6 membered rings. I'll give you credit for that. But if you didn't, you might want to.